Okay, so an exponential function is basically any function. So you have, function means you have two variables, x and y, or whatever your two variables are, where the variable, the independent variable, is in the exponent position. Okay, so a function in which independent variable is in the exponent position. Okay, so for example, y equals 2 to the x. That is an exponential function because my unknown is the exponent. Okay. Sometimes this might be multiplied by a number. In fact, very often it is. So you might also see something like this, y equals 3 times 1/5 to the x. Okay, that's fine as well. You can multiply the power by a number. We're going to see what happens when we do that throughout the rest of today's class, hopefully. In general, in this course anyway, it's going to take this form. Y equals a, some number, times b to the power x. Okay? Now, again, if you move on and you take other courses, you may learn about some transformations to this function. Transformations, you would have seen that in previous courses with quadratic functions. Basically means you take the graph, you move it up, or you move it down, or you move it right or left, or maybe you flip it, that kind of thing. Okay? So we can build from here, but not in this course. We're just going to stick to things of this form. Okay? So what I want to look at first is to consider the effect of changing the base. The base is this b value. So in this example, the base is 2. In this example, the base is 1/5. Okay, so what I want to do is look at two functions, h of x equals 4 to the x, and g of x equals 1/4 to the x. And we will graph these using technology, but I actually want to start out by making a table of values and just see what happens. Okay? Because I think it's easier to understand why the graphs look the way they are if we can make a table of values. So I'm going to make a table of values, and it's actually, I'm going to try and keep track of, well, no, let's actually do it in two separate tables of values. Okay? So we'll do x and h of x, which is 4 to the x first, and then we'll do another one with x and g of x. Okay? So let's say we start at x equals -2, -1, 0, 1, and 2. Okay? If x is -2, h of x is going to be 4 to the -2. How do we interpret that? How do we interpret 4 to the -2 or evaluate it? Dealing with a negative exponent here. How would we figure out the value of that? Yes? Not quite. Not quite square root. Yeah? Yeah, so if it's negative in the numerator, it becomes positive in the denominator. So this is 1/4 squared, which is 1/16. Okay? 4 to the -1. What's the value of that? 1/4, 1/4 to the 1, or just 1/4, 1/4, right. Okay, this is 4 to the 0. What's the value of 4 to the 0? 1. And 4 to the 1, 4 squared, 16, right. Okay, So I am going to, maybe in a different color, make a table of values now for g of x. Okay, and I'll use the same x values. Okay, so when x equals -2, this is going to be 1/4 to the -2. Well, how do I evaluate that? Think about it this way. Oh, yeah? If you distributed this in, you would get 1 to the -2 over 4 to the -2. Okay? What is 1 to the -2? 1. Okay? Now I have a negative exponent in the denominator. So how do I make it positive? Move it up. Yeah. 4 squared. So this is now 16. Okay? So what do we think 1/4 to the -1 is? 4. Yeah. Right? The other thing, by the way, is if the base of your power is a fraction and your exponent is negative, you can just write the reciprocal of the base. So it's the same as 4 over 1 to the 1. This one would be the same as 4 over 1 squared. 4 over 1 squared is 16. Okay? So yeah, this is equal to 4. What about 1/4 to the 0? What's that? Yep, that's 1. What about 1/4 to the 1?
4.
1 over 4. And 1/4 squared. 1/16, right. A quarter times a quarter is 1/16. Okay, so something going on here, right? When the base becomes the reciprocal, suddenly the negative values of x sort of swap. Okay, so we're going to look at this graphically and see what happens. And I know that this is on your next page, but I do kind of want to graph it by hand, just because, again, it gives you a really good understanding of what's going on. Okay, so here's 0, -1, -2. 1, 2. Let's say up here is 16, 8, 4. Okay? So if I'm looking at the first function, h of x equals 4 to the x, what was the value of the function when x was -2? Four to the -2. What did that equal? Right, 1 over 16. So when x is -2, here's 1, here's 0. 1/16 is like right over here. It's almost touching the x-axis, but not quite. Okay? What about when x was -1? 1 over 4. So that's, again, just a little higher. When x was 0. Yep, it was 1. When x is 1 rather, h of x was 4. And when x is 2, h of x is 16. So that's way up here. Okay, so this kind of looks like this. Okay, now as you move from left to right, every time I move over 1, I keep multiplying by 4, right? So think about it this way. A 16th times 4 is a quarter. A quarter times 4 is 1. 1 times 4 is 4. 4 times 4 is 16. The next one would be 64, because it's 16 times 4. So we can think about it that way. We can also think about going this way. As you move from right to left, you're dividing by 4. So this is 1/16. The next one is going to be 1/16 divided by 4. The next one will be whatever that is divided by 4. I keep dividing by 4, dividing by 4, dividing by 4. Okay? Will I ever hit 0 here? No. You'll never hit 0. You're going to get really close to it, but you're never actually going to hit 0, because if you take a positive number and keep dividing by 4 over and over and over again, you get something really, really, really tiny, but it'll never actually be nothing, right? So one analogy that I always think about is, and this here I'm thinking about halving rather than quartering, but I remember when I was a kid, my older sister would like always save half of something. So there'd be like a piece of cake, and she'd be like, I'm just going to eat half. And then she'd go back and say, I'm just going to eat half of this, and half of this, and half of this, and half of this. You actually, theoretically, always still have a little bit of cake there, right? But in reality, that little bit is so small that it's essentially nothing. Does that make sense? Yeah? Okay. So this line is going to continue, and it's going to get infinitely close to, but never touch the x-axis. Okay? As we move into the positive x direction, this is just going to shoot up. Because when you start multiplying by 4 consecutively, you are going to get really, really fast growth. Okay? Now, this line, this x-axis over here, that the graph gets really, really close to but never touches, has a special name. This is called a horizontal asymptote. It's kind of a funny name, but that's what it's called. Okay? We don't talk too much about asymptotes in this course, but again, if you move on, you'll look a lot more at asymptotes later. Okay? But that's basically an asymptote. That's how you would spell it, is a line that the graph gets really close to but never touches. Okay? All right, now let's think about h of x. So this is g of x, right? G of x was a quarter to the x. G of x equals a quarter to the x. Okay, so for g of x, when x equals -2, what was the value of g of x? It was 16, that's right. Okay, so there we go. And when x was -1, what was g of x? 4. So that's right here. And when x was 0, 1. That's where they meet. When x was 1, g of x was a quarter. And when x was 2, g of x was 1/16. Okay? So this graph is actually a reflection in the y-axis. We get this reflection in the y-axis. Okay? And now the horizontal asymptote is on the right side. Okay? So really sort of the important thing here is that when you have a number that's bigger than 1 and you keep multiplying over and over by that number, if I multiply by something bigger than 1, what happens to my original number? Let's say I multiply by 5. I keep multiplying by 5. What's going to happen to my original number? multiply by 5, and then I multiply by 5 again, and then I multiply by 5 again. Yeah, it's going to shoot up, okay? So I end up getting an increasing function when I multiply by a number bigger than 1. If I multiply by a number that's less than 1, like between 0 and 1, like let's say I'm having something, and I keep having over and over and over and over and over again, what is going to happen to my original number? It's going to get smaller, 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 smaller. Exactly. So, and that is true in general for any base. When your base is greater than 1, you get something that looks like the black graph because it's increasing. When you multiply by something bigger than 1, you increase. When you multiply by something less than 1, between 0 and 1, like for example, halving or quartering, you're going to get smaller and smaller and smaller and smaller and smaller. You're never actually going to hit 0, but you're going to get very, very, very small. So you're going to get this decreasing function. Okay? So let's move on to the next page and just summarize some of this. So we kind of got, this was our general picture. This guy was g of x, and this guy was h of x. Okay? So let's pick apart some properties of these two graphs. Okay? So for h of x, oh, I messed up. I'm sorry. This is, I swapped them. Let's swap those back. Okay, so this guy is h of x. This guy is g of x. Okay. For h of x, what is the domain of this function? Look at the arrows and think about where they're pointing in the horizontal direction. So I'm looking at this guy. What horizontal direction is this arrow pointing? Left. And this one? Right. So I got an arrow pointing left, arrow pointing right. What is my domain? Right. X is an element of the real numbers. Okay. What about my range? Yeah.
Y is greater than 0.
Right.
Not equal to.
Exactly. Y is greater than 0, but not equal to, because it's never actually going to touch 0. Gets very close to it, but never hits that x-axis. Excellent. My range is just y is greater than 0. Okay? What would the x-intercept of this graph be? Yeah, there is no x-intercept. If it never touches the x-axis, right? So this is where we have that asymptote. Okay. What about the y-intercept? 1. Yeah. Whoops. What happened there? The y-intercept will be 1 because anything to the power 0 is 1. And remember that the y-intercept is when x equals 0. Right? So if x equals 0, we're putting a 0 into our exponent position. That means the value is going to be 1. Okay, what about g of x? What's the domain for g of x? Yeah, same thing. X is an element of the real numbers. What about the range? Y is still greater than 0. X-intercept, same thing. And the y-intercept, still 1. So there's a lot of properties that are the same, right? The important piece, though, the important piece, and this is what I want you to sort of take away, is that depending on the value of the base, we are either going to get an increasing function or decreasing function. Okay? So if b, the base, is greater than 1, right? That means that I'm multiplying by something more than 1. What's going to happen to my numbers? They're going to, yeah, it's going to increase. So if the base is greater than 1, I'm going to get this. Okay? If the base is between 0 and 1, essentially between 0 and 1, then it's going to go in the opposite direction because now I'm multiplying by something less than 1, so I get smaller and smaller and smaller and smaller. Whoops, that actually touches, but there we go. Okay. Now, exponential functions are only defined for positive bases. Okay. If we had a base of 0, 0 to whatever is just 0. Okay, so that's kind of boring, to say the least. And then if we have a negative base, the value of the function is actually going to keep flip-flopping between positive and negative. Because if you square a negative, you get a positive. But if you cube a negative, you get a negative. So we don't define exponential functions for negative values. So the smallest that it will be is it has to be greater than 0, that base value. Okay? All right. So far, so good? Okay. So the next thing I want to talk about is what if we multiply the function by a number? Okay? In these previous examples, h of x, really, and g of x, what we're doing is we're going 1 times 4 to the x, or 1 times a quarter to the x. So that a value that's built into the equation was just 1. Okay? Let's see what happens, though, when we change that around. Okay, so on a calculator now, let's actually graph all of these. So we've got 3 to the x, f of x equals 3 to the x, g of x equals 1/3 to the x. Okay? K of x equals negative 3 to the x, and p of x equals negative 1/3 to the x. Okay? So before we actually go there, I want to be really explicit with, if you're in this format, what is the a value and what is the b value? If you're looking at f of x equals 3 to the x, that 3 is actually the base value because we keep multiplying over and over and over by 3, right? The exponent applies to this 3. So if I want to sort of put in an a value, it would be 1 times 3 to the x. So here my a value is 1. If I look at the next one, same sort of idea. This is also 1 times 1/3 to the x. Okay? If I look at my k of x, what is the base for this function? It's actually not negative 3. It's still just 3. Yeah, if it was negative 3, the negative 3 would actually have to be in brackets because the x applies to only what comes right underneath of it. Okay? And what comes right underneath it is just the 3. So if I look at k of x, this is negative 3 to the x. That's the same as negative 1 times 3 to the x. Okay? And then finally, p of x equals negative 1/3 to the x, which is negative 1 times 1/3 to the x. Actually, I'm going to write that underneath because it's going to run into my graph. Whoops. Okay. So let's go ahead and graph these using technology. I'm just going to use one calculator for today because I think that the people with the Casio, correct me if I'm wrong, you're pretty comfortable just graphing basic functions, I think? Yes? Okay, cool. And most of you guys have TI, so I'm just going to use this. So the first one was 3 to the power x. Second one was negative 3 to the power x. The next one was 1/3, so 1 divided by 3 to the power x. I think I might be doing these out of order, but anyway. And the last one was negative, in brackets, 1/3 to the power x. Okay? And I'm going to go zoom standard 6. Okay? So we get this, there's a lot of reflection going on here, right? But we get these few graphs. So if we just copy this out, this one was the f of x. This one was g of x. Okay, and then if we keep going down, k of x looks like this. And p of x looks like this. Okay? So here's my question. We're playing around a little bit with bases, taking reciprocal bases and things like that. But we're also playing around with the a value, that number that you multiply the power by. In 2 of them, the a value is 1. And in 2 of them, the a value is -1. Okay? So what I want to know is, where do you see that 1 and -1 values show up in the graphs? Yes, it's the y-intercept. Exactly. Yeah. Okay, so that a value, when it was 1, that's 1 is the y-intercept for both of those functions. When it was -1, we basically get everything, all of our y values become negative. That was the y-intercept for those functions. Okay, so the a value, if y equals a times b to the x, then a is the y-intercept. Okay? And actually, we can see this algebraically as well, because the y-intercept occurs when x equals 0. Okay? So if I take this function and substitute in a 0 for x, b to the 0 is equal to 1. So this becomes y equals a times 1, which is just a. All right. So that's the important piece around that a value, right? When we're looking at exponential functions, basically there are 2 parameters that's going to make one graph different than the other: the a value and the b value. Okay? So the b is our base, and essentially the distinction that we want to make there is the base greater than 1? Because then the whole thing's going to increase. Or is it between 0 and 1? Because then the whole thing's going to decrease. So that's one parameter. The other parameter is what's the a value. And the a value graphically shows up as the y-intercept. And those are the only 2 things that make one exponential function different than another exponential function. Okay. Oh, here, we have another one. So I'll tell you what. Let's just predict what's going to happen with all of these functions. Okay? So here we're again investigating the a value and just changing it around. So in f of x equals 2 to the x, we can actually think of this as 1 times 2 to the x. So here a is 1. The base is 2. If the base is 2, is the function going to increase or decrease? It's going to increase, exactly. What is the y-intercept going to be? For this first one? 1, yeah. So here's 1. And this is what f of x is going to look like. Okay? In g of x, we still have that same base of 2. So that means our graph, again, is going to increase. But for g of x, what will our y-intercept be? For the next one, g of x equals 2 times 2 to the x. Yeah, it's going to be 2, right? So this will be g of x. Okay? And then for k of x equals 5 times 2 to the x. Again, base is 2, so it's going to increase. What's the y-intercept going to be? 5, right? So 3, 4, 5. So this will be k of x. And then for p of x, yeah, it's going to be negative 2. So if the y-intercept is negative, right, what's going to happen is that we're going to flip this downwards. All of the original y values are going to become negative. So we'll see that. Okay? Now, in reality, we don't see negative a values very often, particularly in this course, because we're looking at applications. And when we're thinking about applications, typically we're looking at the first quadrant. Okay? So we don't usually see that, but that's what would happen. Okay? A value in the exponential function is equal to the y-intercept. So that we already sort of discussed. Okay? Questions so far? All right. So, oh, this got cut off. You know what? I'm going to do this. Okay. So C and D look like this. Sorry. D is like this, right? I think. Okay. So here's one question. A painting was purchased in 2012 for $10,000. If the painting appreciates in value at 5% per annum, that's what the divided by A means, per annum, an annum is a year, then which of the following graphs best models the value of the painting for the next 40 years, where X is the number of years since the painting was purchased and Y is the value of the painting? Okay? So this is a painting. You bought it for $2,000 or $10,000. It appreciates. What does appreciate mean? Goes up in value. Yeah, it goes up in value at a rate of 5% per year. Okay? Well, since we know that it appreciates, we can cross this off. It's not D, because D is going down. Okay? If it's increasing at 5% per year, is that going to be exponential growth or linear growth? Linear. Okay, so let's say you have $100 and it appreciates at 5% per year. What are you going to have the next year? 105. Okay, the year after that. It's not it's 105 plus 5% of 105. Yeah, so it's not linear. It's not linear. So B and C are both exponential. And they're both increasing. How do we know which one is right? You said it was C, and you're right. Why is C right and B wrong? Yeah?
Yeah, I was going to say the value of the painting is at the 10,000 and not 0.
Yeah, exactly. We have to think, what's the initial value of the painting, right? Here, time is 0, this is 10,000. In this case, when time is 0, the value is 0. So this is out as well. So it's got to be that one. Okay? All right. Next question. Match the exponential functions with its corresponding graph and justify. So we've got 3 different equations and 3 different graphs, and we need to match them. Okay? Now, one thing that should be in here that is not in here that I'm going to add is that A is a whole number. So a whole number is like 2, 3, 4, 5, 6, whatever. Okay? Okay, so let's see if we can do this. So we've got y equals 3 times 0.a to the x, y equals 4 times a to the x, and y equals 4 times 1 over a to the x. Okay? So can anyone match one of them up? Yep. Yes, this guy matches here. How do you know? Yeah. This is the only one where the y-intercept is 3, and the a value is 3. Okay? So that's one reason. Okay? The other thing that we could say, though, is because we're doing 0.a as our base value, if a is a whole number, it's going to be like 0.1, 0.2, 0.3, 0.4, okay? A also has to be, or 0.a, which is our base number, a number between 0 and 1. And so we are going to have a decreasing function, okay? So the base 0.a is between 0 and 1, so decreasing. Graph is decreasing. Okay? All right, now the last two. Y equals 4 times a to the x. Which graph is that going to be? Yeah, the third one, right? Yes. So how do you know it's the third one? Right, yeah. So the base a is greater than 1, which means the graph should increase. Okay, and then finally this last one is this guy, right? And that's similar to this one. Here, if it's the base is 1 over a, think about that like 1 over 2, 1 over 3, 1 over 4, that kind of thing. The base, again, is between 0 and 1, which means it's going to decrease. Okay, so this is actually kind of similar to the question on that polynomial functions quiz, where you're making a clear connection between an equation and a graph and justifying it. Okay, any questions with that? Awesome.